Good morning, Year 9s. Welcome to the start of probability. As you notice, I'm away today. I'm at a conference in the Gold Coast. It's a tough life. And you should be sitting down with your notebooks open as if this was a normal flipped learning video. Your title today is probability, but don't start taking notes just yet. So, introduction to probability. Today we'll go through the general concept of it, then some definitions, and a couple of practice questions. Now, you'll have done probability before, and you know that some probabilities are really quite easy to estimate. So the most famous one perhaps is, what's the probability of flipping a head on a fair coin? Well, one side head, one side tails, that's one side out of two is a success for us, so a half. So, meaning half the time you get a head. Also, this can be expressed as 0.5, as a decimal, or as a percentage. So 50% of the time we score a head. Similarly, on a dice, rolling a 6 happens 1 out of every 6 times, on average. As a decimal, this is 0.1666, goes on forever, or approximately 16% of the time do we roll a 6. Now, those are very easy to estimate, but probability can also be used to estimate scenarios that are slightly more difficult to calculate. Say, for example, what's the probability of me sleeping in the next 24 hours? Now, most people think this is absolutely guaranteed, so it's 100%, but theoretically there's a chance that I don't sleep. My house burns down, etc., and I won't get to bed for the next 24 hours. Unlikely, but theoretically possible, so we can't give this a probability of 100%. Instead, it's more likely to be a 0.9999, or 99.99% chance happening. That means it's almost guaranteed. Something that's guaranteed to happen is 100%. Alright, now let's take a speculative guess. For example, what is the probability that Shaylee is playing a computer game right now? I'm not sure. Let's give it a guess. What, 30% chance? 40% chance? Who knows? Hopefully she's sitting down taking notes like the rest of you. What's the probability of Mr. Budenberg winning the lottery? Well, I don't even buy lottery tickets, so this one truly is 0. No percentage chance at all of me buying a lottery ticket. If I did buy a lottery ticket, my probability of winning would be pretty close to 0, but technically not 0 because it would be something closer to this, 0.0001, probably a few more zeros in there for that matter, or percent. Sorry for the mess. Essentially, the chance of winning a lottery ticket is extremely low. In fact, it's probably a similar chance of me dating Taylor Swift. Not theoretically 0, so I will give myself a chance, but let's be honest, it's got a lot of zeros. So, 0 is no chance of something happening, 1 is 100% certain it will happen. In between there is almost every event in life, whether it's something that's extremely unlikely, like this, or something that's extremely likely, like me going to sleep tonight. Now, let's go some loose definitions. And I say loose definitions is because I'm not going to write down the formal definition, because most of these are just common sense. Please take notes, and as I'm talking, write down your own loose definition to remind you what each of these words mean. Starting off with, a trial can be essentially anything. So, a trial is flipping a coin, rolling a dice, picking a card from a deck of cards. It's just something that will produce an outcome. Leads us to the next point. Outcome, event, result is the final result of a trial. So if I toss a coin, the toss is the trial, the landing on heads or tails is the result. If I roll a dice, the roll is the trial, the number that comes up is the result. Those two are very loose. Sample space is rather more exact. Sample space is a list of all possible outcomes. So for example, a sample space for a dice would look like this. 1, 2, 3, 4, 5, 6. They are all the possible outcomes in a dice. Now at this point someone in the class is normally being a smartass and saying, oh, what happens if it spontaneously combusts, ha ha ha, so there's like a fire here as well. No, don't bother. realistically, the sample space is 1 to 6, and we just leave it as that. Equally likely outcomes. Doesn't really need a definition. So here, each number of our sample space is an equally likely outcome for a dice. There might be some dice that are weighted or have magnets on them where not every outcome is equally likely. Complementary event. Complementary event is the opposite to a result that you're looking for. To explain it more clearly, let's pretend I want the probability of rolling a 6. So the probability of rolling a 6 on a dice is 1 in 6. The complementary event to rolling a 6 is not a 6. And the probability of rolling not a 6 is 5 out of 6. So complementary events is defined by this not. So the complementary event to me tossing a head is tossing a tail. The complementary event for me picking a heart out of a deck of cards is not picking a heart. And complementary events always add up to 1, because essentially either one will happen or the other will. In a dice, I'll either roll a 6 or I won't roll a 6. So one of these events is guaranteed to happen, so together they add up to 1. Probability of rolling a 6 is 1 in 6, probability of rolling not a 6 is 5/6. They're complementary events. Now, formal definitions. There are 2 definitions for probability based on whether it's theoretical or experimental. Now, theoretical probability is when we don't need to conduct any sort of experiment. We know almost by instinct or theory that some results, that we know the probability by instinct. So for example, rolling a dice, we know the probability of any one number is 1 in 6. Tossing a coin, it's a half. Picking a deck of cards out, it's picking a heart out of a deck of cards, it's 1 in 4. Because 1 in 4 cards in the deck is a heart. So the probability of an event is the number of successes, and that is outcomes we're looking for, over the total number of equally likely outcomes. Using our card example, say we're looking for the probability of picking a heart out. There are 13 hearts in a deck, so that's the number of successes. And we divide that by the total number of equally likely outcomes. Ignoring jokers, there are 52 cards in a deck. So the number of total outcomes is 52. If we were going to list every outcome in our sample space, there would be 52 of them. And the number of successes is 13. We can simplify this fraction to 1 in 4, or a 25% chance of picking a card. Experimental probability is where we don't know the probability for certain. We use our past experience of what has happened to estimate probability. So, sorry Shaylee, I'm going to use you again as an example. If over the last 100 lessons I have turned around and seen Shaylee on computer 12 times, this here would be our total number of experiments, and this here would be our total number of trials. 12 out of 100 is 0.12, or 12%. I would then estimate the next time I walk into class, there is a 12% chance of me seeing Shaylee on a computer. So experimental probability is based on our previous experience. And the definition is number of successful trials over total number of trials. Another perhaps more abstract example would be if I don't know how many cards are in a deck, or if I just pick a random set of cards and I remove cards, say 50 times from the deck, each time I put them back. And of those 50 times, 5 of them are hearts. I could say, well, that's 0.1 or 10%. I could estimate the next time I put my hand in this particular deck of cards that's clearly been rigged with less than normal hearts, I would guess that there is a probability of pulling out a heart of 10%. Alright, so 2 types of probability. One is theoretical, where we can theoretically judge an event because we know generally outcomes are equally likely. The other is experimental. So this can be used for anything as simple as I've driven to work 100 times this year, 13 times I've stopped at the traffic lights. Therefore tomorrow I'd estimate that there is a probability of 13% that I'll have to stop at the lights again. Right. We'll skip that one. Go to this one. Now I'm mentioning decks of cards a lot. It's because from now on after year 9 it's generally assumed that you know what a deck of cards looks like, how many cards are in it, and how many of each type are in it. Which I realise not everyone knows, so it's good to go through it now. Right. Probabilities. What is the probability, if we pick one card out, that it will be a Queen of Diamonds? Well, there's one Queen of Diamonds, she's right there, out of a total of 52 cards. So the total number of possibilities is 52, and there's one possible success. So the theoretical probability of picking out a Queen of Diamonds is 1 in 52. Now, secondly, a red king. There's a King of Diamonds and a King of Hearts, so there's 2 possibilities out of 52, which we can simplify to 1 out of 26. And by tradition, we leave our answers in fraction form, and we leave them in the simplest form possible. I'm running out of space here. So, a jack or a queen. There are 4 jacks and 4 queens, meaning there are 8 successes out of 52 total cards, or 4 out of 26, or 2 out of 13. Note how what I'm doing on the top and bottom to simplify is taking out a factor of 4. So our final answer would be 2 out of 13. I managed to skip B, apologies. An ace. There's 4 aces out of 52, which is the same as 1 out of 13. 1 in every 13 cards in the deck is an ace. A red card. Well, there's 26 red cards, so 26 out of 32, or a half. E, jack or a queen, we did that. F, any card except a 2. Now this is when complementary events come in handy, because you could count every card except a 2, which would give you eventually, well, 48 cards, or you could recognise that of the 52 cards, 4 of them are 2s, therefore 48 out of 52 are not 2s. So any card except a 2, there's a 48 out of 52 probability of doing that. Out of 13. Any card except a jack or a black queen. Well, there are 4 jacks, 2 black queens, which means there are 6 cards we don't want. So our successes would be, there are 46 successes out of a total of 52 cards, and we would simplify that down. I've run out of space, but I'm sure you can all do H. Can you please do those questions during this class? Hopefully I'll be able to get the videos for next week to you, so you should have 2 or 3 videos on a USB going around the class now. Remember to watch them, take notes as you normally would for our flip learning before class next week. Goodbye.